Hello everyone, my name is Sajid Muslehi, and in this video I'm going to talk about modeling multi-phase fluid flow in porous media in Python. Different from my previous videos where I always used the MATLAB Reservoir Simulation Toolbox, which uses the MATLAB language to model different processes in porous media. Here I'm going to use Python for the first time. Before start talking about the code itself, let me talk about the folders that I have shared with you here. So if you want to look into the scripts, I have created a folder here, and inside this folder we have different folders again. This is actually a simulator that I wrote from scratch. The first version of the simulator was this, and it consists of a few scripts to model multi-phase fluid flow, and it is developed in a very simple way, but in a way that you can easily change and adjust to make it work for what you want to have. For example, this simulator now works for one-dimensional porous medium, but you can easily change it to make it work for a multi-dimensional porous medium. So let's get back here. The difference between the first version of the simulator with the next ones is that this one, I believe, is a little bit faster because actually the code is written in a more efficient way. And so I decided to, and because it is more efficient, in order to make it more efficient, I added a few pieces of code, and it made the code a little bit complex. So I decided to remove that complexity. And actually, this is the simpler version of this simulator. But these two are a little bit slower than the first simulator, but simpler. If you want to start looking into the code, I suggest that you start with these two. And the difference between these two simulators is that the mass conservation equations in this simulator is written in mass, for example, in kilogram, but this one is written in mole. But the results of these two simulators shouldn't be different, okay? And I will show that to you later. So we also have some other scripts inside this folder. These are some scripts that actually work with open darts. And I have used these scripts, and I have used open darts to actually validate the results of my simulator, and I will talk about that in the next videos. And this is actually, I will talk about the rest in the next videos later on. So let me start with this simulator, which is the simplified version of this simulator, and the mass conservation equations are written in mole. So let's get back to PyCharm and start with this folder, and the main file that is the file that we are going to run. So as I said, here we have a one-dimensional porous medium. Our system consists of multiple components. We have multi-phase fluid flow, which is miscible. So we have the transport of components between the phases. And in this case, we have used constant K values, but you can use equations of state to actually work with variable K values. And our simulator is isothermal, which means that we have not included any energy conservation equation in the simulator. And the governing equations are solved fully implicitly using the Newton-Raphson method. And in the Newton-Raphson method, we need to construct the Jacobian matrix. And to make it happen, we need to have the derivatives of the governing equations with respect to the primary variables. And to do that, we actually have differentiated the governing equations numerically. In other words, we have used numerical differentiation in this simulator. In MRST, we use automatic differentiation, but here we use numerical differentiation. And as I said, we use mole in this simulator, and actually, depending on what you want, you can even use megamole, kilomole, or mole. But it's not going to change the results of the simulator at all. It may have impact on the performance of your, and actually the stability of your simulator, but it shouldn't have actually any effect on the results. So these are actually the scripts that I have imported. This script, which I have here, contains the units that I may use in the simulator. Here I have a script which defines the reservoir geometry. I'm not going to actually talk about the scripts themselves, but you can look into them, and if you have any questions, you can actually raise them in the comment section. And using this script, we define the fluid model, and here we have our main script, our primary script, in which we have the governing equations, and we actually calculate the residual equations that we are going to have. And in the simulate module, we actually solve the equations. Here we solve the equations, and we have a number of for blocks and if blocks to see. In this if block, for example, checks if the solver has converged or not. And yeah, in this script, we just try to solve the governing equations using the Newton-Raphson method, as I mentioned before. And this script is used to create time steps in an increasing way. We start from small time steps, and we use this actually script to increase the time step size over time. And after a while, the time step size, when the target time step size reaches, that stays constant. All right, at the beginning, we similar to MRST, we define the domain. Grid cells must be identical, and domain must be one-dimensional for now for this simulator, but you can develop it and make it work for actually more complex domains. We have 10 grid cells in the X direction, 1 grid cell in the Y direction, 1 grid cell in the Z direction. The total length of the model in the X direction is 50 meters. The total width of the model in the Y direction is 5 meters, and the total height or the total thickness of the model is 5 meters. And so we give these data as input arguments to this class, and we get an object of the class here as an output argument. So we're done here with the geometry. We start specifying the rock properties. I'm not going to go through these things again, because the way I have developed this simulator, this simple simulator, is very, very similar to what we have in MRST. So if you watch the previous videos, I have talked about how I have written the code. So Here we specify the rock properties, rock permeability, porosity, the reference pressure, and we give these, and the rock compressibility. We give these input arguments to the constructor of the class, and we get an object of the rock. So as you see here, we have a class for the rock, and we get an object of that. Here we specify the fluid properties. This line here, we have the components that we have in the system, CO2 and H2O, the names of the components. Here we specify the names of the phases that we have. We have gaseous phase and liquid phase. This gaseous phase is actually, I'd better say, CO2 rich phase, and this liquid phase is actually the aqueous phase. So this liquid phase is mainly water, and it can also have some dissolved CO2 in this scenario. And the gaseous phase is actually the CO2 rich phase, and it can have some vaporized H2O. All right. So in this line, we define our evaluator for flash calculations. Here we specify the evaluator for the density of the phases that we have. In this two lines, we have specified the evaluator for the viscosity of the phases. What I have done here is very, very similar to what we do in actually in darts. Let me show you the website. Darts. Of course, this is the web page of the research group, but the repository is here. The way I have defined the fluid model is very, very similar to what we do in Open Darts, which I'll probably talk about in the future. And we have ignored the effect of IFT on the system. Here we have defined actually an evaluator for the phases using actually the Brooks and Corey model, for relative permeability of the phases. And then we place all the objects inside this constructor, and we get another object here, and we place them here, and other things are done here, and we get this object and we place it inside our main object, which is the reservoir model. So here we put a reservoir geometry, which we defined here as an object, as an input argument of this, the constructor of the class. And we also defined rock, fluid model, fluid property, evaluator, and we also specify if the system is isothermal or non-isothermal. As I said, the simulator only supports isothermal scenarios for now, and the system temperature is specified here, and we also specify the very, very small values for pressure and composition, for Z and pressure, because we need these values to numerically differentiate the governing equations with respect to the primary variables. And in this section, we have defined the initial pressure, set initial pressure here, and also the initial composition. So set initial conditions for a one-dimensional horizontal domain. This is the initial pressure, which is considered to be equal to the reference pressure, 200 bar. And here we have considered that we have water, we have pure water, in the porous medium, and so the value of the mole fraction of CO2 in the porous medium is very, very small, which we could say that we have water in the system. So these are the initial conditions, initial pressure and initial mole fraction of CO2. We don't need to specify the mole fraction of H2O because we only have two components. And if we specify the mole fraction of CO2, we don't need to know. It is already known. The value of the mole fractions of H2O is already known because the summation of the mole fractions is equal to 1. So here we specify the boundary conditions. To define boundary conditions, I have used very, very large volumes at the boundaries of the domain. Actually, here I set the pore volume of the 0th cell to a very large volume, and also the volume of the last cell is set to a very large volume. And the pressure of the first cell, their 0th cell, which has a very, very large volume, is 50 bar, is actually 250 bar, which is going to drive the fluid into the reservoir, into the porous medium, because we have a higher pressure in this cell. And here we set the pressure of the last cell 50 bar less than the reservoir pressure, which is 150 bar. And because the volume of the cell is very, very large, it doesn't matter how much fluid flows into the cell, and so the pressure of the cell stays constant because we have used a very, very large volume for this cell. And the same thing happens to the to this cell, which has a very, very large volume, and so the pressure of the cell remains constant, even though fluid is flowing out of that grid cell. So here we specify the mole fraction of CO2 in the 0th cell equal to 1, almost 1. So what's happening here, we're actually injecting CO2 into the porous medium. And we have, I could say, a constant pressure boundary on the other side of the domain. Here we specify the time step sizes that we're going to have. For the simulator, the total simulation time is 100 days. We use this function, generate ramp-up time steps, to generate ramp-up time step sizes. This is the total simulation time. This input argument is the maximum time step size, and this input argument is the number of ramp-up time steps. So after 50 time steps, we will reach this maximum time step size, and after that we use the same time step size until we reach the total simulation time. And here we specify some information about the solver. The maximum number of Newton-Raphson iterations is 50. The Newton-Raphson tolerance is 10 to the power of -5, and we place them in this dictionary and put and this is the dictionary that we have, and we place these arguments as the input arguments of this function. Initial conditions, reservoir model, DT, and solver are all the things that we need to have for our simulator. And after that, once we run the code, all the things are done inside this function. The equations are being solved. The residual equations are being evaluated, actually. the Jacobian matrices are constructed and the system is solved. And you can look into that to see what is exactly happening. If you have any questions, just place them in the comment section. So what you see in the terminal is that, so this is what we had at the beginning. Between these two dotted lines, we have the information of one time step. And each line indicates the information of one iteration. So as you see, between these two lines, the time step counter stays constant because this block is actually for that time step, for example, for this time step. And for this time step, as an example in this case, we needed to have 3 iterations to solve the equations. And this is the residual, the norm of the residuals that we have, and this value should be less than 10 to the power of minus 5 Newton-Raphson tolerance to make sure that the solution has converged. And this is the runtime of that iteration. And what we see here is the runtime of this, the whole time step. And this is the total runtime. So let's have a look at the results. To visualize the results, we open this module and run it to actually, let me remove these figures. So this is what we have as output here. This is the pressure profile. This is the pressure of actually the leftmost grid cell, which has a constant pressure of 250. And this is the pressure of the last grid cell of the model, which has a constant pressure of 150. And this is the CO2 overall mole fraction, at the end of the simulation. As you saw, we specified the overall mole fraction of CO2 equal to 1 for the leftmost grid cell, and actually for the last for this grid cell of the model, the concentration of CO2 does not change. At least it's not sensible because the volume of this grid cell is very, very large. And so its pressure doesn't change. Also, the pressure of this grid cell doesn't change. And the same things happen to the concentrations of the components. In these two grid cells, we should not see any change over time because their volumes are large. So this was actually the result of this simulator. If you run actually the same thing in this simulator, you will realize that the results of this one and this simulator, which is written in kilogram, the results are the same. And that is something that we expect to have. And if you run this simulator, we will also have the results over time. Let me also run this simulator. So this is the pressure profile at the end of the simulation. This is the pressure profile at the end of the, the overall mole fraction profile along the porous medium. At the end of the simulation, it is not over time. I should remove this. This is at the end of simulation. And actually what you see here is the evolution of pressure in the porous medium. This is quite the beginning of the simulation. And as we go upward, the simulation time goes on. And what you see here is the CO2 overall mole fraction. Actually, the x-axis is the cell indices. And we can visualize it like this because we have a one-dimensional model. And this is the CO2 overall mole fraction profile. over time. And as you see, the front of CO2 moves to the outlet over time. And this is the saturation of the CO2 rich phase over time. This is the CO2 mole fraction in the gaseous phase over time. And this is the CO2 mole fraction in the liquid phase over time, which you can see yourself on your system by running the main actually module here. And after the results are stored, you can run this script to check the results and change it in a way that you want to have. All right, so I hope that this was something helpful and useful, and hope you enjoyed it, and hope you're having a great time.